Thank you so much for being here, and over to you.
Thank you very much. And it's very nice to have been invited here. I will explain in a bit what this title is about. First, I will just start by saying something about myself, because I'm pretty sure we don't know each other, except us.
But, so there's more people coming, actually.
Yeah. So I'm a professor in the Department of Computer Science, and I've been there around 10 years now. However, my research has pretty strong links with mathematics. I have a background in philosophy and in mathematics, especially mathematical logic. And my research is in theoretical computer science. So I mostly work in the foundations of programming language theory, and I develop formal methods for various fields, including artificial intelligence, programming, and others, using as tools algebra, logic, and more specifically also category theory as a unified mathematical language. What I'm going to show you today has to do, as the title suggests, with linear algebra, which I'm pretty sure is a course that all of you have taken. Probably in your first year you've seen at least a bit of linear algebra. And the reason is that linear algebra is extremely ubiquitous in mathematics, in science, in engineering. Is it the basis of quantum theory, of the analysis of cyber physical systems, or the analysis of artificial intelligence, in machine learning. So we really do a lot of linear algebra. We can say, in a sense, is the workhorse of science. Now, at the same time, I claim that linear algebra is typically presented to you in a rather unappealing way. You are taught how to do matrix multiplication, study orthogonal projections, eigenvalues, eigenvectors, and so on. But it all feels very algorithmic. And also rather cumbersome, both in notation and the kind of calculations you are doing. I would argue that, in a sense, we are working at a level of abstraction which is not exactly suitable for humans. And I will make the analogy, for instance, with what happens in music. If you want to enjoy music, if you want to play music, you typically look at a score. You don't just register with your brain the sound waves that a certain musical sound does. That's not really tailored for human understanding, right? So abstraction matters, and the language you choose for a certain topic really matters in the way of enjoying it and exploiting it. A similar example, which perhaps is closer also to your experience, is with programming. When you're taught programming, you're typically taught it for the first time in what is called a high-level programming language. And this is the kind of programming languages that most people are accustomed to, things like Python, JavaScript, or even just Java, C, C++, and so on. All these are high-level languages in the sense that they abstract away from how the underlying machine, the hardware, actually computes with the variables you are allocating, with the functions you are defining. And this is in contrast with other languages, typically much older, like assembly, for instance, which instead allow you to actually inspect bit by bit what the hardware is doing on your memory locations. So here is the same specification written in Python and in assembly. You see, one is actually immediately understandable, even trivial. The other one, not at all. One is made for humans, the other is not. And I will argue that linear algebra is in a similar situation. So when you're taught linear algebra as you're typically taught, I'm arguing that it is as if you were to learn programming languages by being taught assembly. It's like the first year in your programming course, they teach you assembly as your first language. That's not what should happen, right? I'm saying the same works for linear algebra, and as a matter of fact, you see a reflection of this sentiment in the way people actually work with linear algebra. Many people like to work with linear algebraic calculations in a more abstract way, using, for instance, graphical models, quantum circuits, or a signal flow graphs, other kind of circuits models and graphical models. these are all models whose behavior is typically interpreted as a linear algebraic entity, a subspace, for instance, a system of equations. But you don't see that kind of system of equation. You work instead graphically. You emphasize resource connectivity, exchange of information between components. What I'm arguing is this is the level of abstraction we should work with. However, we should have a language which is abstract, which is tailored specifically for linear algebra, is not dependent on any specific application, and it's actually completely formal, because sometimes these graphs are just graphs. You cannot do much with them from an algebraic viewpoint. So we want these two things together. And this is the answer provided by this framework called graphical linear algebra. So this framework came to the fore about 10 years ago now, 12 years, and has been quite popular in the meantime. It is a high-level language for linear algebraic calculation, is a formal language, at the same time is a graphical language, as the title suggests. How can it be graphical but formal? Because it is rooted in category theory, and more specifically in the formal language of so-called symmetric monadal categories, which are the so-called string diagrams. Now, even though graphical linear algebra is rooted and justified in category theory, I'm not going to give you a 1-hour lecture about category theory. I will assume you know nothing about category theory, and everything I will say will stay kind of above it. I will just have a single slide in which I clarify a bit the category and theory underlying it, but is by any more needed for understanding what's going on here. Okay, so I will begin by showing you this graphical linear algebra, or GLA. For first of all, we will study exclusively linear maps and matrices. Then we will see how it can be extended to subspaces. So basically to talk about anything linear algebra, because anything can be understood in terms of subspaces. And finally, we'll see some applications of linear algebra to various fields of science and engineering. So, to start with, linear maps and matrices. So, well, this is not... Okay. I will just use this. As I said, everything we're doing is rooted in an even more elementary language, which is the so-called language of string diagrams. So as I said, this is based on category theory, which we won't pursue, but if you want to know more, these are, for instance, a couple of introductions to the subject. Generic string diagrams are a formal language in which your basic entities are these boxes. They depict some kind of process, which we'll have to interpret for now, and this process has interfaces on the left and on the right, which are these dangling wires here. So I put some dots as well, just to say that I'm not telling you exactly how many dangling wires there are, but you can imagine there are like 7 wires on the left and 5 wires on the right. And these are the interfaces. Sometimes the process is a function, so you can think of the ones on the left as inputs and the ones on the right as outputs, but some other times it's not necessarily a function, it could be a relation, for instance. So it's best to leave it not, let's say, committed to a specific interpretation. There are two fundamental ways in which these string diagrams compose. The first is sequentially, provided that the C process has the same number of dangling wires on the right as the D process has on the left. And instead, I can always do this, namely put them one over the other. So this corresponds to a sequential composition of processes. I first execute C and then I execute D. And this is a parallel composition. I execute C and D independently. There is now some basic wiring, because what we want to do is not just to work with these labels, but we want to introduce some elementary building blocks, allowing us to build more complicated string diagrams. So this is what we are doing right now. We are going to introduce building blocks necessary to construct richer and richer fragments of linear algebra. We start with extremely elementary kind of building blocks, more technically from an algebraic viewpoint, we may call them operations or generators, which are these three. This is the intended semantics, okay? The first one swaps two elements, so you see that x goes down and y goes up. The second one is just an identity wire, okay? It moves x left to right. And the last one, I could have written just nothing. I put this dashed line just to say this is like the empty diagram. It has 0 ports on the left and 0 ports on the right. The typical thing we will add is that these operations do not come alone, but they always come together with equations. And equations are there to tell us when two string diagrams should be taken with the same meaning. This equation, in particular, is telling us that if we twist two wires 2 times, this is like not twisting them at all. Okay? And this is different from instance from not theory. Everything here is a planar graph. I also want to point to the fact that in this equation you see the first more complicated string diagram built using the sequential and parallel composition. You see the first one is based on a parallel composition of 2 instances of the swap above, and the one on the right is a sequential composition, and this is the parallel composition of 2 identity wires. Okay? Now, so far this does nothing. It just moves information from one part of the diagram to the other. In order to do linear algebra, we need some extra operations, and it turns out we just need extremely little. So that's the cool thing about GLA, that you actually can found the entirety of linear algebra basically on addition and copy variables. That's all you need. So we start with addition. Addition is 2 operations. The first one, you see, has 2 interfaces on the left, and if you have 2 values x and y, the idea is that this works as an addition, so it gives you on the right the sum of x and y. And this other one has no interface on the left, so nothing comes in, and what comes out is the constant value 0. The equations are telling us the following. This one is telling us that this addition operation is commutative. The second one is telling us that the 0 is the unit of this addition operation. And the last one is telling us that this addition operation is associative. So if you have these 2 operations as these 3 axioms, what algebraic structure you have got yourself?
What algebraic structure?
Yeah, with these 2 operations and these 3 equations. Sorry? Not quite. You have no inverse. A group needs an inverse. Field is a lot more stuff than this. This is just a commutative monoid. Okay? It's just a commutative monoid. To have a group, you would need an inverse.
Yeah.
But here there is no inverse. Okay? Now, as I promised, we only need another pair of operations, which are copy operations. And this may come a bit weird for you, because when you do algebra, copying variables is no big deal, right? If I have x, I can use x twice in an expression. But here, in string diagrams, everything is resource sensitive. So when we copy a variable, we have to make it explicit. And this, of course, comes very handy when you do processes that are sensitive to resources. Imagine you're doing quantum theory. Now you have these theorems about no cloning, no deleting. So you need an explicit copy and discard operation because your resources are valuable in the system. That's the idea. And it's the same, of course, in linear algebra, where the concept of linearity, namely, you only use each variable exactly once. So, contrary to traditional algebra, in graphical linear algebra, we have explicit copy and discard. So the first one is a discard. You see that I get any x and I discard it. The second one is a copy, so I get an x. And on the right, you see I duplicate the value x. The equations now are quite similar, but you see they are rotated. They are reflected corresponding to the one on the y structure. If you remember, the y structure was pointing in this direction. This is pointing in that direction. So is not quite called a monoid, is what is normally called a comonoid. Is not an algebraic structure, is a coalgebraic structure. If you have done some off-algebra theory, for instance, you have encountered algebra and coalgebras, this is an example of a coalgebraic structure. In the setting of string diagrams, we don't care if something is algebraic or coalgebraic, we just take everything in. These equations in particular are saying that copying is associative, that this card is the unit for copying, and that copying is commutative. Okay? Next, we need these two operations to interact, these two classes of operations to interact. So we have introduced all operations we need, and now we make copy and discard interact. First of all, you see that if we have a 0 and we copy it, is the same as just having two zeros. And here, if I take x and y, I do their sum and I discard it, it's just as discarding x and y. The one below is telling me something about copying the sum of x and y. I can do it in two different ways and they are equivalent. And the last one just tells you that if you have a 0 with everything, you can just discard it. You're not going to use it in the computation. And these equations also have a name, which we didn't come up with, which is the equations also called bialgebras. So the remarkable thing is that so far, all the structures we have introduced are structures that are well studied in the literature. Monoids, homonoids, and they interact as bialgebras. Having given these generators, these operations and these equations, we can already encode natural numbers. How do we encode natural numbers? The first on the left is the number 0. You see, you receive an x, you gave out a 0. Second one is number 1, x to x. This is number 2 because you see you copy x and you sum, so what you get on the right is 2x. What we have there? Number 3. This is 3 copies of x. And you can imagine how this goes on, right? As a matter of fact, we can introduce some syntactic sugar and say number 0 is defined like this, and number k plus 1 is defined as number k together with an extra floor, right? The semantics of a generic such diagram will be given an x and multiply it by the natural number x. So you see we already were able to encode natural numbers without adding them, just by representing them using copy and discard. There are some other equations that now we can prove based on the equations we had before. Notice these are derivable equations, namely we don't need to introduce them, but we can derive them from the previous one. The first is saying that we can sum two numbers. This one is multiplication of two numbers. You may call them scalars if you like. This is saying a scalar gets copied if it meets a copy, and this is that two scalar, if I have the same scalar, then I can move it past the add as well. So having all these in place, we are now ready to represent matrices. This is how a matrix looks like. So this is a 2 times 2 matrix. So what's the pattern? What you see on the left, these ports, they represent your columns. And the ports on the right, they represent your rows. The first column, you see that if you follow the path from the first column to the first row, you get an A. From the first column to the second row, you get a C. From the second column to the first row, you get a B. And from the second column to the second row, you get a D. Okay? And this is reflected by the semantics in the sense that if you take two inputs, x and y, and you regard that as a vector, then the vector you get out is exactly the multiplication of that vector by this matrix. Okay? So because we can compose string diagrams, now that we have matrices in isolation, we can actually also study them together. So something I don't show here is that if you put them in parallel, this corresponds to the direct sum of matrices. And if you put them in sequential composition, what does this correspond to? It corresponds to matrix multiplication. So let's see how this works. Suppose you have a 2 times 2 matrix and you put it together another 2 times 2 matrix. Now using the equations we add, we transform our string diagram, it becomes this. And this is exactly the 2 times 2 matrix that represents the multiplication of those 2 matrices. So what we did at each step, first we used this law here. You see that these parts in the middle have become these parts here. Then we have used this one to move the A, B, C, D past this black structure. Then we have used this to move this past the white structure. And here we have multiplied scalars together. Any questions so far? Or things that are unclear? Okay? So, this is not by accident. In fact, we can prove the following result. The string diagrams are in one-to-one correspondence with matrices, provided you quotient the string diagrams by the equations of bialgebras. So these equations we saw before, monoids, comonoids, and bialgebras, they are needed in order to ensure that 2 string diagrams that represent the same matrix are made equal. So if you take string diagrams modulo these equations, then they are in one-to-one correspondences with matrices. The left wires of your diagram corresponds to the columns, the n wires of the diagram, the right wires of the diagram correspond to the rows. So what we have here is just natural number matrices, but we know that loss of linear algebra, of course, takes place in different kind of structures. No? It would be pretty limiting if we only could do natural numbers. It's not, in fact, hard to generalize it to any semi-ring, not just n, and these include, for instance, fields, like the real numbers. So how does this work? Well, the difference is just that we cannot treat any more scalars as syntactic sugar as we did with the natural numbers. If you remember the natural numbers, we just defined them in a derived way using copy and addition, but we need to introduce them explicitly. So what this means is that it means that next to these 4 operations that we introduce a scalar operation for each scalar in the semi-ring. So this is a one-to-one operation. Was semantics is to map x to k of x. So it is the same thing as with natural numbers, but we need to introduce them explicitly. Okay, and the same equations hold. An interesting phenomenon that happens once you do this is that among these semi-rings, if your semi-ring is actually a ring, so it has a -1 element, this -1 plays the role of the antipode. So the antipode is this special element that certain structure called off-algebras has, which cancel out your algebra and co-algebra. So what this means in string diagrams is that if you copy and discard with a -1 in the middle, you destroy your structure. So what's going on here is that this wire is just 1, and here we are using the actions that says that if I have k1 and k2 in parallel, I do their addition. So 1 plus -1 is 0, and this is an axiom. Okay? So this is just to say that while we work with a ring, we don't just have bialgebras, but we have these things called off-algebras. Does any of you have encountered off-algebras in your studies? No? What kind of mathematicians are you? What do? You just do analysis, you just do calculus? Or?
I read it second year, so I guess.
Oh, in second year.
Where do you think algebras come?
Well, have you done any also algebraic geometry or algebraic topology?
No, that's in third.
They don't
Okay.
come in algebraic geometry either.
Okay. Anyways, this is just to justify, because later on we'll call these structures off-algebra, so you at least know what they are.
Okay.
They are a bialgebra with an antipode. As a matter of fact, it's maybe a good thing that you haven't seen them yet, because when they see them, sticking to my initial introduction, they will get much more complicated than nice pictures. All right, so we have the same kind of theorem as before. String diagrams for modulo of algebras are in correspondence with matrices over that ring. Now that we've done matrices, we want to move to something more serious, because as you know, linear algebra is not just about linear maps and matrices. If you want to study kernels, if you want to study projections, orthogonality, determinants, and all that stuff, we need to work with vector spaces, and in particular with the notion of a subspace. So our next goal is how can we extend our language so that it's actually expressive enough to talk about subspaces, which is something we don't do just yet. It turns out, quite remarkably, that we don't really need anything new. What we need is just to take the existing operations that we have introduced, those 5 above, and introduce 5 more operations which are exactly the one above, but at the mirror. So the semantics of this is exactly the same as the semantics of the one above. It's just that instead of reading them left to right, you have to read them right to left. So you can still regard them as functions with inputs and outputs if you want, but the inputs and outputs roles are reversed. Flow is flowing in this direction here and in this direction there. So what should you do if you have in your theory functions and functions pointing in the other way? What you should do is just discard the idea of a function and just talk generically about relations, right? Both things, you can understand them as relations. Now, of course, these are not just any relations, but because they are linear maps, they are linear relations. What it means to be a linear relation, it means you are a relation that is also a subspace. So it is closed under the addition and the scalar multiplication of the ring you're considering. Okay? So this is how the semantics works. So now our operation will not just mean linear maps, but linear relation or subspaces if you prefer. And what can we do now that we have introduced these extra operations? Because I have to convince you we can actually do subspaces. For now we just have these weird things flowing in the wrong direction. So to convince you of that, let's first look at the concept of a kernel. So how is the kernel of a matrix? We have a matrix. This is, for instance, the matrix 1, 2, 3, 4. It's a 2 times 2 matrix. The kernel is the set of all vectors such that this matrix multiplied by those vectors is equal to 0. Gives you value 0, right? This is the kernel. And this is a subspace. How does this work in graphical algebra? It works very easily. You just add these pins. So you tap out your diagram, and this tapping out just means that here you are collecting all vectors such that those vectors multiplied by this matrix are equal to 0. Because remember, the semantics of this is saying this is 0. So when you plug them, it's like if you're putting a constraint. You're saying the value I receive must be 0. So the semantics of this diagram is exactly the kernel of the matrix M. It's a set of vectors such that M of V is equal to 0. Let's see another example, the image of a matrix. Once again, we have the same matrix. The image is just obtained by tapping out, but in a dual manner. So instead of tapping out with white here, we tap out on the left with black. What is the meaning of that? Remember the semantics of this black unit. It says any value. So you have to imagine that this is like is generating any possible value in your field or ring or whatever you're fixing in the structure. So this is saying, give me here any outcome that the matrix multiplied by some vector can give me. And this is precisely the concept of an image. So the semantics of this is the collection of values MV for any V in my ring. Okay? Now, you know that any subspace can actually be represented either as an image or a kernel of some matrix. So this is in fact sufficient to show you that any subspace is representable in this theory. And what is also remarkable that I want you to notice is this duality. You see that for a kernel, we added a white on the right, and for an image, we added a black on the left. So you see, this theory that we are discovering is extremely symmetric. There are all these internal symmetries that have to do with left, right, black, and white. And we'll see more later. And the nice thing about graphical linear algebra is that it makes you discover all these symmetries that are completely covered if you just do linear algebra in the usual way. So in this theory, there is a duality, an internal duality between taking the image or taking the kernel of a matrix. Another symmetry that transpires is the one of the equation that transpose. So what is transpose graphically? Transpose corresponds to flipping scalars and swapping colors. So I have a matrix, all the black becomes white, all the white become black, and now if I read this in this direction, this is precisely the transpose matrix of that matrix there. So just another symmetry that is present in the theory. There are many more things we can show. We can show Gaussian elimination, we can show orthogonal projections, we can show determinants. There are many things, and later at the end I will give you sources for that. I don't have the time to show you everything, but just to mention there is more you can do. Okay? The thing I want instead to focus on now is what equations we need. Because everything we've seen so far is how can we use these 10 operations to represent images and kernels. But as for linear maps, these representations are not unique. We need some equations that tells us when two string diagrams are representing the same subspace. And what are these equations? So let's make a bit of recap where we are so far. The first one above, the first line, we have already seen. It obeys the equations of Hopf algebras. This we have seen in the first part. No? So we have a monoid, a comonoid, bialgebra equations, equations of interaction with the scalars. Okay? This is Hopf algebras. Which equation we should impose on the ones below? Well, because they are just reversed, we don't need to do any effort. We just take the equations of Hopf algebras reversed. And this is again an Hopf algebra actually. It's just that the role of the comonoid is played by the white structure, the role of the monoid is played by the black structure. But it's still an Hopf algebra. Okay? So we don't need to prove anything new so far. The trick, the novelty comes from the interaction, because now we have two structures in isolation, but how do they interact together? Well, it turns out their interaction is extremely lean. In particular, we just need to comment on the interaction of the white structure together, of the black structure together, and on the scalars with the rest. So the white structure together, they form another well-known and well-studied algebraic structure called Frobenius algebras. Frobenius algebras is another structure, just like Hopf algebras, that I'm pretty sure we'll encounter at some point in your studies. They are encountered a lot in topology, for instance, in algebraic topology. They are fundamental in the study of cobordisms. They are fundamental also in quantum theory. Frobenius algebras, for instance, model quantum observables. What it means to form a Frobenius algebra for these string diagrams. What these equations allow you to do is to stretch your string diagrams in various ways. You see, this is saying basically that I can bend my white structure whatever I like, and then preserving equality. The only rule that matters is that the topology of the diagram needs to be preserved. As long as the interfaces are untouched, the internal structure can be morphed as you like. The black is another Frobenius algebra. And what about the scalars? Well, for the scalars we have to say something interesting. Namely, they give rise to fractions. And this is unavoidable, okay? If we want to be complete for subspaces, we need to talk about fractions in our theory, and we talk about fractions in the following way. We want to express the fact that P backwards has the same meaning as 1 over P. So P times 1 over P is 1, and 1 is 1 over P times P. This is what these two are saying. And these are just ways of flipping between black and white structure. Okay? These allow you to convert the white and the black Frobenius algebras one into the other. if you add an antipode, a -1. Okay? And this is the full picture. So here I'm putting together everything we have done. Hopf algebras, Frobenius algebras, and fractions. And this theory is complete for subspaces. So as you can see, the remarkable thing is that this thing is incredibly symmetric. We have a theory, we have its dual, we have Frobenius for the white, we have Frobenius for the black. So everything is very much symmetric and dual, which is quite magical. Okay, this doesn't happen often. And as a matter of fact, you can even characterize these equations below as arising from a distributive law between the two Hopf algebras. So if you've done rings, you know that the theory of rings is a distributive law between an abelian group and a monoid. Here is the same thing on steroids, namely Hopf algebras. I have a distributive law between Hopf algebras, and they create this structure here. So these structures are telling you how the two Hopf algebras interact. Yes?
When you had the two algebras, the two structures in isolation, the explanation before was there's flow going from the left to the right and right to the left. How does that work with when you combine them together?
Yes, so as I was saying, this is one way you can look at it with the flow, but as a matter of fact, when you look at them together, you should abandon flow altogether, you should just think about relations. It's the same as imagine to put together functions in one way and functions backwards. If you put them together, you lose any sense of inputs and outputs. You have just to talk about relations. So these are like sets of constraints, if you like. And if you think about systems of equations, that's exactly what these are. No? A system of equations is a set of constraints. Any other questions?
Sorry,
Yes.
how are they different, especially when you put them together? So you just think of them as relations. How are they different exactly to functions? Sorry.
Well, the thing is, you cannot think anymore of your semantics as a function. Because, think about this one, okay?
Yeah.
The semantics of this one is, if I have an x on the right, I have two x's on the left.
Yeah.
How is that a function? A function doesn't constrain its inputs, no? It's like a function that is only defined if its inputs are both at the same value, and in that case gives you that value. So it's not a total function anymore.
Okay.
So, yeah. Okay. But it's okay, because it's a relation. It's a relation between the pair xx and x. Yeah. All right, so we have the same theorem, we achieve the same theorem as before. There is a one-to-one correspondence between our string diagrams and subspaces. There are two caveats. The first one is string diagrams are now modulo equations of interacting Hopf algebras, which is this theory here, these equations here. This is the theory of interacting Hopf algebras because, as I told you, these extra equations arise as a distributive law telling you how the two Hopf algebras interact. So the correspondence between string diagram modulo interacting Hopf algebras and subspaces of K. And what is K? K is the field of fractions of R. Because remember, we introduce fractions in our theory, right? The moment we have scalars pointing left to right and scalars pointing right to left, is unavoidable that we are thinking about fractions. So what is happening is that the theories in isolation, they talk about a ring or a semi-ring, but when you put them together, you are talking about a field. And this is the field of fractions of that ring. Field of fraction is just a notion, okay, that exists in linear algebra. And your ring, in order for that to work, needs to be a principal ideal domain. But this is typically not a problem. For instance, polynomials, they form a principal ideal domain. Okay. Right, so now I have a single slide where I show you the category theory underneath. Okay? So this is just in case you're vaguely familiar with category theories. So the string diagrams generated by those 5 generators and these operations, they form the morphisms of a category. And this category is a symmetric monoidal category, which means it has sequential and parallel composition and symmetries, and we call it Hopf. When we put together this one, and we do string diagrams over those generators and we quotient by these equations, that category we call int of R. When I say that these string diagrams have a semantics, what I mean technically is that there are functors from the category of R to the category of matrices, and from the category int of to the category of subspaces. Okay? This is what it means rigorously and formally when I say, oh, the semantics of this and that, and when I write this red stuff. All right? And when I say there is a one-to-one correspondence, what I mean is that these functors are actually isomorphisms of symmetric monadal categories. Okay, so there is a correspondence in a very strong categorical sense.
This might be difficult for you to explain, but what is a functor? Sorry.
A functor is a transformation, a mapping of objects and morphism of one category into objects and morphism of the other category that preserves the categorical structure. If you think about monoids and monoisomorphisms, a monoisomorphism is like a function that preserves the monoid structure. Here is the same. A functor is a transformation that preserves the category structure. Okay, so it's the notion of function but adapted to the realm of categories. All right. I also want to show you a proof in GLA. So there will be a few unsaid in this proof to make it a bit more simple, but bear with me. So the thing we want to show is a very simple result in linear algebra, namely that if a matrix is injective, then its kernel is 0 and vice versa. Is this something you can prove? Okay, you find it in textbooks. So first task is how do we represent this proposition even? Well, first of all, the matrix A is just a generic matrix. We use that notation with the A seen as a scalar, but you have to think of that as your matrix A. And the wires there, they are a bundle of wires. So I have as many wires as I need as left and as many as I need on the right. Okay? I just don't write them all for simplicity. Then, when I say its kernel is 0, what this means is that I need to prove, or I can assume the equation that A composed with the co-unit, the y co-unit is equal to the y co-unit. So this is saying that the kernel of A is this diagram on the left, is 0, which is the diagram on the right. Okay? How do we say that is injective? Injective means that a matrix multiplied by its inverse matrix is equal to the identity. The inverse matrix, you can show that is the same as the matrix A pointing in the other direction. So saying that the matrix A is injective, it means to say that A composed with A pointing backwards is equal to the identity. Okay? So these are our two statements, and we want to show that they are equivalent. And these are the proofs. So let's focus on the left first. Here we're using our assumption. Sorry, not our assumption. Here we are using the fact, this is an axiom of the theory of Hopf algebras reversed. The theory of Hopf algebras reversed says that we can cancel out any backward scalar, so we can cancel out also any backward matrix. So this means, applied here, it means that when we have this identity can become A. And the second step here is just our assumption. So in this direction of the proof, we are showing this statement, assuming this statement. So this is the assumption that A with A is the identity, and they cancel out. Let's see in the other direction. So we start with A and the A, and we want to show that they are equal to the identity. First of all, here we are applying the Frobenius, some derived law of the Frobenius structure. So you see that what we are doing is to take our A and stretching it out. Okay, this is what's going on there. Then here we are transforming this part into white, and we have to add a -1 to make it work. Then we can move these two A's along this addition, and we get a single A here. And at this point, we can use our assumption to make it disappear. And at this point, this white really becomes black, And using Frobenius, I straighten it out, and it becomes an identity again. Okay? Of course, I skipped a few intermediate steps, but this is just to give you the flavor of how we can prove the actual theorems in graphical linear algebra. And there are a few papers that detail this in much more rigorous language. Okay? All right. So we are, let's say, at the peak, at the summit of our mountain. We have characterized subspaces. We have done the world of linear algebra using string diagrams. Where do we go from there? So first thing I want to mention is some extensions that are notable. First of all, we have something called graphical affine algebra. This is just an extra operation which has no input, a single output, and the single output gives you a 1. So in this theory, is not anymore linear algebra you're doing, is affine algebra. Affine algebra, you can always translate things by a certain quantity, and this one helps you with that. There are some extra equations you need, and if you impose these extra equations, then you are in one-one correspondence with affine subspaces. So this is how you do affine algebra. Then you can do quadratic algebra. What it means to do quadratic algebra, it means you have an extra operation that gives you the value 1/2 x squared. So if you think about just classical linear algebra, you cannot do quadratic functions. But quadratic functions are important. Think about convex optimization, for instance. Okay? So in quadratic algebra, you can do quadratic functions. You have extra equations. And you are in one-to-one correspondence with quadratic subspaces, which are the solution of quadratic optimization problems. Another notable thing is that the matrix fragment, so the linear maps fragment of this theory, is in one-to-one correspondence with Gaussian probability. And in that case, the interpretation you give to your operation is this notation here, which means it's the standard Gaussian probability. Okay? So you can give this theory two different interpretations. One has to do with algebra, and the other has to do with stochastic processes, which makes it quite interesting. And I will come back to that later in an application of this. Okay? The extra equations are also cool. This is what is called the Maxwell-Herschel theorem, which says that these values, these quadratic functions, are rotation invariant. So this is a rotation matrix. You see that there are sinus and cosinus appearing. All right. So we'll conclude by giving you a gallery of examples of graphical linear algebra in action. So I will gloss over many details. Okay. So don't be too confused or puzzled if some examples speak more to you than others. Okay. I will purposefully be a bit, let's say, bird's eye view here, but I really want to give a broad overview of what goes on in this field. Our first application is control theory. In control theory and engineering, people use a lot this kind of formalism called signal flow graphs. A signal flow graph is a signal processing circuit where you can think of information as flowing in the circuit left to right. And there are two notable things. The first one is that there are feedback loops that can feedback signal, and there are registers that can store the previous part of the signal for future use. So there is a notion of memory in these circuits. Well, it turns out every signal flow graph can be translated into a string diagram. And you see the string diagram reflects the shape of the signal flow graph. Here I put these red lines to show you how the individual operations participate together in forming the signal flow graph interpretation. So you see that there is a Frobenius algebra structure on the black that gives you this feedback loop. There is addition, there is copy, and these axes are there because the ring you have to fix to get the semantics of linear flow graphs is the polynomial ring over the reals with one indeterminate x. So this x appears as a scalar, and this interpretation is a one-place memory location. The semantics of the string diagram reflects the behavior of the signal flow graph. So signal flow graphs are traditionally interpreted as linear dynamical systems, so as systems of difference equations, and the semantics of the translations, the semantics of the string diagram is the difference equation that represents the signal flow graph. A couple of things you can do with this framework. First of all, you can prove signal flow graph equivalence. Imagine you have two signal flow graphs and you want to show that they have the same semantics, they interpret the same behavior. Well, you can translate them into string diagrams and use the equational theory that we saw before to transform one into the other. And doing that using the equations means what you are doing is to show that these two diagrams have the same semantics. Another thing you can do is going from a specification to its implementation. So this is something that is done a lot in the theory of linear dynamical systems. You start with a fraction, okay? This is a rational fraction, a fraction where both values, the numerator and the denominator, are elements of the polynomial ring. And what happens is that you want to create a signal flow graph whose behavior the signal is processing is the expansion of this fraction as a formal power series. So you know that such a fraction can be expanded into a formal power series. This formal power series defines a function, and the implementation we want is a signal flow graph that computes that function. You can do that using string diagrams. So you translate your fraction into a string diagram. So you can recognize here that the part above this x is here, it points in this direction, and the denominator here points in the opposite direction. So the 1 is this layer, minus x is the second, minus x squared is the third. And then you transform it until you reach something which looks exactly as your string diagram. And there is a theorem saying that you can always do that in this theorem interacting of algebra. You can always pass from a fraction to its implementation as an executable signal flow graph. Another example I want to show you, electrical circuits. If you look at graphical affine algebra, you can interpret the components of an electrical circuit as string diagrams in graphical affine algebra. So voltage, resistor, and current. And these will have the same semantics as the original components. So if you know the Kirchhoff's law that assigns to each of these components a semantics in terms of current and voltage, this is the semantics that these string diagrams have in their traditional interpretation. Something nice you can prove with this is, for instance, this is an example of a property you can prove. You can prove that parallel voltage sources of different voltage are disallowed. So if you look at a textbook in electrical engineering, it just tells you disallowed. Okay, it doesn't have a formalism to say is wrong. Here we have such a formalism. So we start with the string diagram that represents two parallel voltage sources. This is the voltage source A, this is the voltage source B, and this is how they're put in parallel. And you transform it, and you end up with this diagram. So this diagram, it represents wrong, because the semantics of it is the empty subspace. The empty subspace is an affine subspace, okay? So the semantics of this is the empty relation. It means this circuit has no real behaviors. It cannot function, okay? Another example, Petri nets. If you're familiar with concurrency theory, concurrent processes, this is even used in other fields like biology, for instance. A Petri net is a model of a distributed system. Petri nets can be interpreted again as string diagrams of graphical linear algebra. The interesting bit is that this part here, these bubbles, can be interpreted in different ways, and depending on which way you choose, it interprets a different semantics of your system. Okay? Oh, you just booked for an hour?
Yeah.
Okay?
Wow.
Well, we will be very fast then. We can have questions in the bathroom or something. So linear regression you can do, okay? So linear regression is the idea is that you have a set of observations in green and you want to approximate a linear model. Here is this line here. You have two ways, ordinary least square methods. You compute a system of equations minimizing the quadratic error, or you have a stochastic method in which you compute a random variable. And now I don't have time to show you this nicely, but essentially the two methods are the same if your error is Gaussian distributed, and you can use graphical quadratic algebra to show this. So in graphical quadratic algebra, you have a string diagram that represents your system with a random variable, and you can show that the solution to that random variable is the same as you obtain with the ordinary least squares. Okay? Unfortunately, I cannot show you much better. probabilistic programming you can do, I will skip that. Other notable extension that I cannot do because also that would be a lot big is ZS calculus. This is the extension of graphical linear algebra to do quantum processes. These are the two textbooks of reference, and this is used nowadays in real-world application like quantum error correction and quantum circuit compilation. These are string diagrams that perform those tasks. So in conclusion, we presented this alternative foundation for linear algebraic reasoning. Whose main appeal, I believe, is that it's abstract, visual, and compositional, and highly modular. It reveals these very nice symmetries and algebraic structure and underpinning algebraic calculation, and it is a unifying framework for many different applications. And I think we can stop here. As I said, I can take, I guess, questions in the corridors. Thank you.